Okay, all right. Mineral families. That's what we call the groupings. We call them families. Um, and minerals, as we put these into families, they're classified by their composition. I would star that, highlight that, whatever you need to do to draw your attention to that. That's kind of an important point. It might come in handy to know that fact at some point in the future when points depend on it. If you kind of get what I'm saying. So when I say that they're classified by composition, what does that mean? What is, the composition? What does that mean? Anyone, or you can put in chat or whatever. If we're talking about the composition of something, what are we talking about? Figured everyone would be awake at 1 o'clock. So if I were to talk about the composition of chocolate chip cookies, there'd be flour and sugar and eggs and chocolate chips. And so if we're talking about the composition of minerals, we're talking about what?
What they're made out of.
Good, thank you. It's what they're made out of, what stuff is in them. So we're going to group minerals by their composition. We're going to group them by the elements that are in them. When we're sorting these minerals and putting them into families, we use the formulas. That's what we look at, but we look at the end of the formula. We're only concerned with the last two elements. So, it could be a formula that's, a page and a half long. We're only worried about the last two elements. The other stuff doesn't matter to us. Or at least it doesn't matter to us for what we're doing. Not to say that stuff isn't important. It is, but what we're doing is just the last two elements. That's what we're looking at. All right, so the first mineral family is the native family, or native group, native element, native family. It's only made of one element. Its composition is just one element. So these are pure substances. When found in nature, they're almost always found kind of by themselves, in pure form. So, here's 6 examples. These are not all of them by any stretch, but these are definitely some of them, and some of the more well-known native minerals. So anytime you see something with a formula of just one element, you know that it's a native mineral. All right. So the native family, again, single element. Here we have 2 different minerals. The one on the left is graphite, and its chemical formula is C. It's just carbon. That's it, pure carbon. Does anybody happen to know what graphite is used for most, as far as we're concerned?
No, pencils?
Right. So it's what we call pencil lead, but it's not actually lead. It's graphite. So graphite is obviously pretty soft. It's obviously pretty cheap, but it is pure carbon. The other picture is a diamond, and its composition is carbon. That's it. So both of these things are made of carbon, just pure carbon. That's it. but they are dramatically different. The reason that they're so different, even though they're made of the same stuff, is the crystal structure. And this is kind of what I touched on yesterday about how crystal structure can affect the properties of a mineral. This is a great example of that because they have the same composition. The difference is diamond forms much deeper in the earth, so there's a lot more pressure being exerted on it when it forms, and that changes the crystal structure. So the crystal structure is different from graphite. Graphite forms closer to the surface, so the carbons form rings, and then the rings kind of form into sheets, and those sheets aren't bound together very tightly. So it's easy for those to break off, which all you have to do is just run your pencil across a piece of paper, and that's enough to break some of those sheets off. And that's we have writing on paper. But I think it's a good example to show they're both made of the same stuff, but how crystal structure can affect the properties of a mineral in such a dramatic way, and the difference between pencil lead and diamonds. All right. So as we get into these other families, something to kind of pay attention to is there are a couple of different kind of patterns that I hope you'll be able to pick up on. It hopefully will help you kind of name or learn how to name these and to put them into the families. So this first one's a silicate. So we have Si and O is at the end, because remember, we're only concerned with the last two elements in the formula. We're not worried about all the other stuff. Another thing is we're not worried about the numbers. We're not worried about the subscripts. So we're just concerned with Si and O. So silicon and oxygen. So whenever there's a silicon and an oxygen, that's a silicate. So in silicate, you get the silic from silicon. So a silicon and oxygen is a silicate. Silicon and oxygen form quartz, which is all over the place. Most sand is quartz. It's what glass is made from. Now, obviously, they don't just grab random sand. I mean, it's purified, and they take out the ones they don't want and all that stuff like that. But that's basically what it is. And if you look at sand under a microscope or magnifying glass, I mean, it really does start to look like little bits of glass, because that's what it is. The silicate family is the most common mineral family. So of all of them, the silicates are the most common. That's another piece of information that I would star, highlight, whatever you want to call it, just to kind of draw your attention to that. Just remember that the most common mineral family is the silicate family. All right, when silicon and oxygen combine and bond and form a compound, they form a tetrahedron. Sometimes you'll see it named, like in this is silica tetrahedron. Sometimes you'll see silicon oxygen tetrahedron. The main thing is tetrahedron. Anytime you see something about tetrahedron, you should instantly think silicates. It's basically this shape. It's kind of like a three-sided pyramid. This one kind of shows a little more information. So with a silicon oxygen in the middle, and then 4 oxygens around it, it forms this kind of pyramid shape, three-sided pyramid. So that's a tetrahedron. So anytime you see tetrahedron, just think silicate. Those tetrahedrons can link up together to form long chains or sheets or rings. There are a lot of variations. and how they can be linked together, which, you know, that's a different crystal structure. So it gives rise to different crystal shapes and different characteristics and different properties. All right, so the next family is the carbonate family. So here we have a C and an O at the end. So we have a carbon and then an oxygen, and that gives us carbonate. So the one before we had silicon, oxygen, silicate. Here we have carbon, oxygen, carbonate. We're starting to see a little bit of a pattern here. Here we have one with sulfur and oxygen at the end. That forms a sulfate. So the sulf coming from sulfur, which is the S. So silicon, oxygen, silicate, carbon, oxygen, carbonate, sulfur, oxygen, sulfate. You see where this is going? And again, we're not worried about the numbers right now or anything like that. And then next one, we have a P and an O, which P is phosphorus. So a phosphorus and an oxygen gives us phosphate. So silicate, carbonate, sulfate, phosphate. And so there's kind of that pattern there. If it has, you know, an oxygen at the end, it's going to be an 8. You know, whatever the element before it, that's kind of the bulk of the name. All right, so on to the kind of the next pattern or kind of subset. So these are the ides. So if there is a metal and then an oxygen, that's an oxide. So the ox coming from oxygen, because that's what's combining with the metal, which in this case is iron. So metal and oxygen is an oxide. The next one, a metal and sulfur is a sulfide. And so with this one, if there's a metal and then an element, then it's going to be that kind of the, you know, piece of that element's name with an "ide" at the end. This one's a little bit different, but not really. The halides. In the little drawing of the periodic table, that yellow column is the halogen group. So it's just a group of gases. The most common are going to be chlorine and fluorine. So if you see a formula like this one for salt, which is, you know, sodium chloride, there was sodium and chlorine. If you have a metal, which sodium is a metal, you have a metal and then anything from the halogen group, but like I said, most commonly it'll be chlorine or fluorine. Then those minerals are in the halide group. So there we're getting the you know, the HAL from halogen, but then we also have the ide again. So this would be a halide family. All right, so for all the families, you can kind of see the patterns here maybe. So that first bunch are the 8s. You know, so silicon, oxygen, silicate, carbon, oxygen, carbonate, sulfur, oxygen, sulfate, phosphorus, oxygen, phosphate. Then you have the next group where it's a metal and oxygen, oxide, metal, sulfur, sulfide, and a metal and a halogen, so either chlorine or fluorine, would be a halide. And then the native, again, that's just, you know, any mineral that has a formula of just one element. That's it. It's a pure substance. All right, so now I'll let you kind of tell me what family these are in. So this first mineral, chalcopyrite. So we have some copper, we have some iron, we have some sulfur. So does anybody have an idea of which family this would go into? Remember, we're only looking at the last two. So we have a metal and a sulfur. So you know it's going to be a sulfate or a sulfide. I mean, there are only two of them with sulfur.
Sulfide.
Good, sulfide, because we have the metal and we have the sulfur. So it's a sulfide. In order to be a sulfate, there would have to be an oxygen at the end. Good. The next one is fluorite. So we have calcium and fluorine. So calcium's a metal. And then we have fluorine, which is in that halogen group. So which family would that be in? A metal and a halogen.
Halogen.
All right, so a metal and a halogen, that's going to give us a halide. It'll be a halide. How about hematite? So here we have iron and oxygen. Iron and oxygen. Good. This is an oxide coming in from the chat. So you have a metal and then an oxygen gives us an oxide. Good. How about galena? PBS, not the one where Sesame Street lives. So lead and sulfur. So lead is a metal and sulfur. It gives us a
Oxide.
say again.
Oxide.
Not an oxide. We'd have to have an oxygen at the end for oxide. The ending's right though. This would be a good sulfide because we have sulfur at the end. So we have a lead or a metal and then sulfur is a sulfide. How about this one? Sulfur. Just plain sulfur. Just a single element. Single element. Good. So this would be a native mineral, just because it has one element. That's it. And sometimes minerals have unique properties, things that are, unique to that mineral. It's the only one that does that. Does anybody happen to know the unique property of sulfur? Anyone? It stinks. It smells like rotten eggs. So not many minerals have a smell, especially one like that. It's so distinctive. Let's see the next one. How about this one? So we have some muscovite mica. Looks like a pretty busy formula, but we don't really have to worry with most of it. So we're just looking at the end where we see that Si and the O. And it tells us it's a what? Si and O. So silicon and oxygen is a not that one. Close. So silicon and oxygen. So since there's an oxygen at the end and silicon's not a metal, you know it's going to be an 8. And since it's silicon, it's a silicate. Anytime you see silicon and oxygen, you should immediately think silicate. And again, it's the most common family. Forms a tetrahedron. And the last one, quartz. So we have silicon and oxygen. Which family would that be in? Silicon and then an oxygen. Since silicon is not a metal and oxygen's at the end, we know that it's an 8. Since silicon is before the oxygen, it's a silicate. Good. SiNO again. Now, if you think back to the notes from yesterday, I guess it was yesterday, and also the Earth Layers project, the pie chart with the 8 most common elements in the Earth's crust, oxygen and silicon were the top 2. Oxygen was almost twice as common as silicon. This is why, because of quartz. So for every quartz atom, or for every silicon atom, you have 2 oxygens. So if you look at the percentages in that pie chart, it's not exactly double, but it's pretty close. And this is why, because there's so much quartz in the crust. And there's tons of quartz, it's everywhere. It's all over the place. I mean, most of it is small, but it's all over the place. All right, are there any slides that I need to go back to? Anyone? Okay.